Welcome to the talk Assessing the Overhead of Offloading Compression Tasks. My name is Laura Bromberger. I'm a second-year doctoral student in the online group of the LHCb experiment at CERN, the European Organization for Nuclear Research. As a doctoral student, I'm working on analyzing compute, storage, and throughput trade-offs of the data acquisition system used in high-energy physics. In particular, I'm researching the usage of data compression in such high throughput environment. In the next 20 minutes, I will present to you an analysis on what performance can be achieved by commercially available compression accelerators in comparison to CPU-only compression algorithms. Utilizing data compression is always a trade-off between investment of compute power and time versus the achieved data reduction. Here, custom chips and accelerators come in handy as they allow to greatly reduce computation time and power consumption for a fixed set of tasks which are hardwired in the chip. However, developing such an accelerator normally comes with great time and money investment. This investment can be reduced when using commercially available accelerators. So in this talk, we therefore will have a look at commercially available compression accelerators, how they perform, and how they compare to CPU-only compression algorithms. The presentation is divided into 5 parts. The first part, we will present to you our multi-threaded benchmarks. In the second part, we analyze the machine utilization, power consumption, and the performance of the accelerator while data is being compressed. And in the third part, we compare the achieved performance to the performance of the CPU-only compression algorithms. This is then followed up by the discussion, conclusion, and the outlook. This work is motivated by CERN's current upgrade effort. At CERN, particles are collided at velocities close to the speed of light to explore rare and unknown quantum mechanical effects. To support higher energy level for those collisions, CERN's experiments are upgrading their detector and all related infrastructures, including the compute farms and software. For our experiment, the LHCb experiment, this means, for example, that we will upgrade the bandwidth between detector and compute farm from 60 gigabytes the second to 5 terabytes the second. In the compute farm, we will run 2 filter stages. The first one runs at real time to do a first selection of interesting collision data to reduce the data so that we write it to a temporary storage at speeds of 150 gigabytes the second. The second filter stage is slower but more thoroughly and does the final selection. It is not possible for the second filter stage to keep up with the first filter stage. Therefore, we need around 100 petabytes of temporary storage to store the data until we find processing time during the downtimes of the particle collider. Now we will first talk about our benchmarks implementations. We have 2 different benchmarks. One is the CPU-only compression benchmark and the other one is the accelerator benchmark. We tried to keep them as similar as possible to reduce the bias introduced by different implementations. On the left, you can see in black all the functions which are available in both benchmarks, and in blue, the additionally added structures and functionality we need for the accelerator benchmark. The CPU-only compression benchmark has 2 types of threads: the main thread, which initializes and controls all other threads, and the compressed threads, which executes the compression and is as independent from each other as possible. There would be 2 naive approaches to do this. First would be to always read small data chunks from the dataset which is stored on the hard drive, and the other one would be to load for each compression thread the full dataset into memory. Both approaches are not feasible because the first one means we get unnecessary latency penalties due to accessing the hard drive. And the second approach is not possible because we do not have enough RAM. So our solution to that problem is that for each NUMA domain, we load the dataset once into memory and then share this dataset with all the compression threads for which are executed on that particular NUMA domain. The output buffer is not affected by this. For the accelerator benchmark, we have one additional thread called QThread, which provides chunks of data in newly allocated memory location to the compression threads. This is necessary as the accelerator does not allow share access to the same memory location which is shared within multiple instances. Another change is that in each compression thread, we now can have multiple compression streams which are executed concurrently on the accelerator. We also use here NUMA binding, but we don't have to do it internally. Here it was enough to just bind the entire benchmark onto the NUMA domain on which also the accelerator is attached to. During our implementation and our benchmarking, we saw the following phenomena, that it is not easy to measure time correctly when you're in a multi-threaded environment, because we want to measure only the sustained throughput. Therefore, we do not want to have any timing in it which includes the initialization time or the release of resources. So what we did is each compression thread has its own internal timer, which will be used for the results calculation in the end, but the main thread will coordinate it. It will start the threads, it will wait until all threads are initialized, and then it will give the go signal to start the compression, and it will then also send the stop signal to all the compression threads. Coming now to the performance analysis of the accelerator. We run all our benchmarks on a dual socket Intel Xeon E5-2630 version 4, which has 20 real cores and a total of 40 virtual cores. And the accelerator we use is AHEI-378 with up to 80 gigabits per second of throughput. It consists of 4 FPGAs, which are up on a half-size double-width PCI Gen 3 card. It supports the compression algorithm LCS and deflate, and for deflate also the data formats gzip and zlib. We chose only to evaluate deflate because LCS has the worst performance and gzip and zlib has the same performance as deflate. For the datasets, we used 7 different datasets. 4 of them were compression corpora and 3 of them were high energy physics datasets. For the compression corpora, we looked for some which are larger than 150 megabytes to account for the big data environment where we're running in. The only exception which we had was Calgary. The Calgary corpus is the most famous compression corpora, so it was also found in many related works. What we did here is we tarred it into a single file and then multiplied it until we reached 150 megabytes. For the high energy physics data, we use data from 3 of the 4 big CERN experiments. For the algorithm, we chose 6 different ones, BSIP2, LC4, SNAPPy, XZ, zlib, and C-standard, and a total of 8 different configurations. In the graphs, you see for 2 different data sets the performance. Each color is a different algorithm, and each point on a line represents a different compression level, which allows a trade-off between compression ratio achieved and the time required for it. In the red circles, you see our selected configuration. Here we try to select levels which are at tipping points for compression ratio or throughput. The best result for the accelerator we achieved when utilizing 3 queue threads, which fill a queue of up to 500 elements of the 2 megabytes chunk size. For compression threads, and each of those compression threads had 12 compression streams in it. The memory bandwidth and power consumption was not influenced on what data set we were running. On the right side, you see the plot. In the plot, the relationship between throughput and compression ratio for each data set. What you see here is that the high energy physics data, LHCb, Alice, and Atlas, had the worst compression ratio and the worst performance overall. But this is not very surprising because the nature of what they are measuring comes close to a random number generator or those quantum mechanical effects. So we cannot expect a high compression ratio for random numbers. Nevertheless, LHCb with 75 gigabits per second still achieved at least 94% of the advertised throughput. Coming now to the comparison. The CPU-only benchmark had the best configuration when running with all virtual cores. We had different CLab version running, but in the end we decided to compare the accelerator against CLab level 2. This was mainly due because CLab level 4 would have been a better choice for the compression ratio, but it had a significant decrease in throughput. For like only up to 7% better compression ratio, the throughput dropped between 13 to 37%. There was also another algorithm which had a similar compression ratio than CLab level 2, but a 2 to 3 point higher throughput, and this was C standard level 2. On the left plot, you see the fastest compression algorithm, Snappy or LC4, depending on the dataset, versus the throughput of the accelerator. Here you see that the CPU algorithm have huge variation between different datasets, and even if you ignore the bad performance of compression ratio, even then the accelerator significantly outperformed those algorithms throughput-wise. In the right plot, you see the compression ratio for each dataset. In red are the same algorithm plotted as on the right side. It's Snappy and LC4 with the best throughput, but with the worst compression ratio. And in orange square, you see the exact opposite. It's the algorithm with the best compression ratio, but with the worst throughput. These were C standard level 21 and XC level 5. And in blue again, the accelerator. There was one outlier, the Calgary corpus. There, the algorithm with a high compression ratio were able to recognize the inner pattern of the Calgary corpus itself. And therefore, they achieved a compression ratio of around 185. The CPU power consumption was for all algorithms between 72 to 103 watts, with CLab level 2 and C standard level 2 having the highest, nearly reaching the TDP of 105 watts, which is 4 to 45 watts more than the accelerator needed on the CPU. The RAM power consumption was more stable in the distribution of which algorithm needs what consumption. Their CLab level 2 had the least power consumption of only 4 watts, while XC level 5 had the highest power consumption of 9 to 11 watts for the RAM. The RAM power consumption for the accelerator was 7 watts. With that, it achieved twice the throughput of the CPU-only algorithms. If the CPU-only algorithm wanted to achieve the same memory bandwidth, they needed 9 watts for the RAM. Overall, the accelerator had an 8 to 17 times higher throughput than CLab level 2. This benefit was especially visible for the datasets with a low throughput and a low compression ratio, namely the high energy physics datasets, here shown in dark blue. Now coming to the discussion. We saw a throughput variation between the datasets of 7% for the accelerator and up to 42% for the CPU-only algorithms. We therefore think that there is some kind of bottleneck in the bandwidth for the accelerator and could imagine that if switching from a PCI Gen 3 board to a PCI Gen 4 board, the throughput will increase. Furthermore, we saw that NUMA binding was very important for stable performance because even if the accelerator was run all alone on the server, it would get throughput drops of up to 10 gigabits per second when not utilizing NUMA binding. We also had a look at related works, though we didn't find so much fitting to our work. What we found were multiple papers implementing CLIP on different FPGAs and then measuring on the Calgary corpus the harmonic mean compression ratio over all the different files. But here we saw that in the end, the AHA 378 has actually a quite good implementation and surpassing both of the papers we found. Furthermore, you see on the right side that C standard level 2 is a good replacement for CLIP level 2 because it has a little bit better compression ratio and a way better throughput. The same kind of holds true for C standard level 21 and XC level 5. We wanted to analyze even more of the server, for example, the cycle activity, to see how efficiently each of the algorithms is implemented. However, sadly, this was not possible as those specific performance counter were not very reliable on that server. Nevertheless, we think we got some interesting results which will help from a system integration point of view to understand underlying requirements to not degrade the accelerator performance. Overall, the accelerator needed only 10% of the CPU compute resources if you expected the data already residing in memory. And it also, and on the other side, it needed up to 80% of the memory bandwidth of one socket. We therefore think that the most compatible task for co-location would be tasks which utilize NUMA binding to prevent unnecessary cross-NUMA domain communication, and tasks which have a high computational load but a very low memory bandwidth requirement. And preferable, it's a task which utilizes compression as a post-processing step so that the data is already residing in memory. We also hope that when switching from a busy waiting communication model to an interrupt-based communication model, we are able to further reduce the resource requirements. We also tested another accelerator, the Intel QuickAssist 8970, which does both encryption and compression with up to 100 gigabits the second as throughput and supporting deflate, GZIP, and CLIP. We tried two different implementations, one with the API and one with the Intel CLIP wrapper, but both were rather unsuccessful, so we decided to not further pursue it because of the significant performance and stability issues which we saw there. Coming to the conclusion, overall, this work provides insights into the integration costs of accelerators. We saw that NUMA binding is important and that measuring time is not so straightforward in multi-threaded environments. The accelerator needed 80% less CPU resources while having an 8 to 17 times higher throughput than CLIP level 2. Therefore, we think that commercially available compression accelerators are a realistic option as they provide the power saving and throughput advantages for well-known compression algorithms, while at the same time one does not have the high development costs. Furthermore, our work on CPU algorithm can also be used to select the right algorithm for the right task. Our study has shown here that independent of the dataset, the relative performance between the algorithms stays more or less the same. Our future goal is to develop a workflow which allows to get a good co-scheduling performance of both the accelerator and the CPU workload. And for this, we first want to implement the interrupt-based communication model with the accelerator and then co-schedule those benchmarks with different CPU workloads and hope to find patterns useful for our idea of an optimal co-scheduling policy depending on the characteristics of the CPU workload.